Good morning, everyone. My name is Moohyeon. The title of this talk is Write-Optimized Dynamic Hashing for Persistent Memory. This work is joint work between UNIST and Sungkyunkwan University in South Korea. The outline of this talk is as following. I will briefly go over some background knowledge about static hashing scheme and their limitation. Then I will explain how the limitation can be overcome with legacy dynamic extendable hashing and briefly review the persistent memory. However, the legacy extendable hashing cannot be used for persistent memory in its current form. So we designed Cacheline-Conscious Extendible Hashing scheme to overcome such challenges. In short, we call it CCEH. After introducing how we designed the Cacheline-Conscious Extendable Hashing, I will present our performance study, then I will conclude the talk. Hash table is basically an associative array that stores key and value pairs by using the hash function. When a hash collision occurs, we create a larger table and rehash all the entries into a new table. This full table rehashing is the most expensive operation in hash table. There exist many methods that try to postpone the full table rehashing. One of the most well-known technique is linear proving. Another one is chaining, and the other one is double hashing, such as cuckoo hashing. However, even if we use all these methods, we still need expensive full table rehashing to accommodate the increasing number of data. The problem of full table rehashing is that some queries that trigger full table rehashing suffer from long tail latency. This graph shows the CDF of insertion latencies of well-known cuckoo hashing and the state-of-the-art hashing scheme for persistent memory, path hashing, and level hashing. In this experiment, query arrival time is in Poisson distribution. These flat horizontal lines are because of the expensive full table rehashing. That is, whenever full table rehashing is performed, subsequent queries must wait in queue and their latency significantly increases. To resolve this problem, several dynamic hashing schemes such as extendable hashing have been used in various file systems and database systems. CCEH is a variant of extendable hashing we designed for persistent memory. As you can see, our CCEH dramatically decreases the rehashing overhead, and its tail latency is an order of magnitude lower than the other static hashing schemes. Before I present the design of CCEH, let me explain how the legacy extendable hashing works. Extendable hashing consists of multiple buckets instead of a single associative bucket. Since extendable hashing splits one bucket at a time on demand, it manages pointer to buckets in a separate data structure called directory. The directory has a global depth, which indicates how many bits are used to find the correct bucket. And each bucket has a local depth, which indicates how many bits are in common. In this example, the global depth G is 2, so we use 2 bits to find the bucket. The middle bucket is pointed by 2 pointers, so any hash key whose postfix is either 01 or 11 is stored in this middle bucket. So the length of this common postfix in the middle bucket is 1. Therefore, the local depth of this bucket is 1. Suppose we insert key 0011. In this disk-based extendable hashing, the common practice is the least significant bits of the hash key are used in the directory as shown in this example. So we use the last pointer in the directory to visit the middle bucket. However, the middle bucket is already full, and we need to split this middle bucket. When splitting a bucket, we check one more bit in addition to the common postfix. Based on the additional bit, we perform rehashing and migrate the key value pairs to one of the split buckets. As we split the bucket, we need to update the directory so that each split bucket is pointed by the directory. Note that we need to update more than 2 pointers, which is not failure atomic. In this example, the overflowing bucket is pointed by 2 pointers, so we don't have to increase the size of the directory. This is a relatively simple example. Consider this case. A bucket overflows, and its local depth is equal to the global depth. That is, if it is pointed by 1 pointer in the directory, as in this example, there is no space for these 2 new buckets, and the common postfix of the 2 new buckets uses 1 more bit than the global depth. Then we should double the directory size to have pointers to these newly allocated buckets. When we double the size of the directory, we use 1 more bit and increase the global depth. Note that even if we double the size of the directory, we don't need to rehash the other buckets. In this example, the leftmost buckets and the second leftmost buckets are untouched. We just allocate new space for the directory and update its pointers. After increasing the directory size, we update the directory entries to point newly split buckets. Now, persistent memory is expected to be fast and byte-addressable as in DRAM. And it is durable as hard disk drive or solid-state drive, which makes it an attractive device for both main memory and storage. The motivation of this work is to design extendable hashing for persistent memory. When designing a data structure for persistent memory, there are some challenges. The first challenge is granularity mismatch between the data transfer unit and the atomic write unit. The data transfer unit between CPU cache and persistent memory is 64-byte cache line, but the atomic unit of bytes is only 8 byte. Another challenge is that the modern processors do not guarantee the order of memory writes. So I've covered background. So from now on, I will present our contributions and design of the Cacheline-Conscious Extendible Hashing. Let me summarize the challenges first. The extendable hashing is designed for disks, and it has been used for file systems and database systems. If we use the extendable hashing as an in-memory index, there are some challenges that we must address. If we use page-sized large buckets for an in-memory index, we have to access a large number of cache lines in a bucket, which is suboptimal. On the contrary, if we use cache line-sized small bucket, the directory will become very large. That is, we need an 8-byte pointers for every 64-byte cache lines. So the overhead of directory management will become comparable to the overhead of a full table rehashing. Another challenge we need to consider is that the bucket split operation is not failure atomic. A bucket split operation requires multiple pointer updates. Without logging, multiple pointers cannot be updated in a failure atomic manner. To resolve these challenges, we propose the Cacheline-Conscious Extendable Hashing scheme. This CCEH has a 3-level structure. We call it, CCEH has an intermediate level called a segment. With this 3-level structure, CCEH can find any data with only 2 cache line accesses. Second, we designed a failure atomic directory update scheme by introducing the split body tree. Third, we introduced lazy deletion scheme for efficient failure atomic segment split. Let me start with the 3-level structure. CCEH uses a small cache line sized bucket. However, we group multiple buckets in a contiguous memory block, which we call a segment. With this intermediate level segment, the directory does not need to have a pointer for each bucket. Instead, each bucket as an entry, each directory entry points to a segment. Using this three-level structure of the directory, segment, and cacheline-sized bucket, CCEH effectively reduces the directory size while keeping bucket size small. Although CCEH uses a large segment, we do not want to access every cache line in a segment. So the question is, how can we minimize cache line accesses? While legacy disk-based extendable hashing uses a hash key just for directory, CCEH uses another part of the hash key to index a bucket in a large segment. That is, a part of the hash key is used as a segment index for the directory, and another part of the hash key is used as bucket index inside a segment. As shown in this figure, the most significant bits of the hash key are used to find the segment from the directory, and the least significant bits of the hash key are used to find the bucket inside the segment. So there is no need to access irrelevant buckets, and we can reduce the number of cache line accesses down to 2. Now, let me describe how CCEH updates directory in a failure-atomic manner. For ease of recovery, we use the most significant bit as the segment index. Then the directory entries for split segment will be located adjacent to each other, as shown in this figure. When a segment split, we check how many directory entries need to be updated. This number can be obtained by comparing the local depth against the global depth. Then we change the directory entry whose index is larger. For example, in this figure, we update the directory entry from the bottom to the top. Then we increase the local depth of overflowing segment. In this example, the local depth of S1 is increased to 2. As you can see, the split history can be shown as a binary body tree. Now let me explain how this body tree helps recovery. Suppose a system crashes while segment S5 splits. We note that each segment should be pointed by 2 to the power of global depth minus local depth directory entries. If this is not the case, we have to roll back or replay the split. As the segment S1's local depth is 1 and the global depth is 3, in this example, S1 must be pointed by 4 directory entries. However, S1 is pointed by only 3 directory entries. We can easily figure out the inconsistency and recover from the failure without explicit logging. This recovery algorithm requires to scan all the directory entries. However, the directory size is usually much smaller than the hash table, so the recovery cost is almost negligible. Now, let me describe how CCEH can further improve the performance of split operation through lazy deletion. This figure shows the legacy copy-on-write split operation. We create 2 segments and copy key values from overflowing segment. With this legacy cow splits, we have to update 2 pointers in this case. For the rock research, please refer to the paper due to the time constraint. In our proposed lazy deletion, we reuse the overflowing segment to minimize the dirty writes. As shown in this figure, we create only 1 segment and copy corresponding key value pairs to it. For the remaining key value pairs, we do not delete nor overwrite it. Instead, we just increase the local depth of the overflowing segment. In this example, once we increase the local depth of the left segment, the common prefix of this segment becomes 00, not 01. Therefore, any key whose prefix is 01 can be ignored and considered as free space. Note that we update only one cache line for this left segment. Compared to the legacy cow split, lazy deletion reduces the number of cache line flushes. Now, I will present our performance study. Our testbed machine has two Intel Xeon Haswell CPU with 8 2 GHz cores and 20 megabytes of L3 cache. It has 64 gigabytes of DDR3 memory, and to emulate the persistent memory, we used Quartz, a DRAM-based persistent memory emulator. We insert 160 million key-value pairs to a hash table for the evaluations. First, we quantify the performance implications of our CCEH design vectors. The left graph shows the insertion throughput of our CCEH and the legacy extendable hashing with varying the size of the buckets and segments for each implementation. As we increase the bucket or segment size, legacy extendable hashing suffers from a larger number of cache line accesses, whereas our CCEH always accesses only a fixed number of cache lines. Therefore, the insertion throughput gap widens as we increase the segment size. And the right graph shows the number of cache line flush instructions for the same experiment. Interestingly, CCEH calls a larger number of cache line flushes. This is because CCEH uses bucket index to find the free space. If a hash collision occurs in the segment, even if there are some other free cache lines, CCEH splits the segments. Although the utilization of CCEH is lower than that of legacy extendable hashing, CCEH significantly outperforms extendable hashing due to the small number of cache line accesses. In this experiment, we varied the read and write latency of persistent memory using Quartz. CCEH is a default Cacheline-Conscious Extendible Hashing, and CCEH-C is a variant of CCEH that uses copy-on-write scheme instead of lazy deletion. Our CCEH outperforms the other static hashing scheme as we minimize the number of cache line accesses with 3-level structure. This breakdown graph shows that the lazy deletion scheme effectively reduces the number of dirty writes by half compared to the copy-on-write split scheme. This graph shows the space utilization of CCEH and level hashing. Due to the full table rehashing, the load factor of level hashing drops down to 50% after each rehashing. However, our CCEH dynamically allocates small segments on demand. Therefore, it shows much smoother curves. Note that our CCEH can employ linear probing inside a segment. If we allow full cache line probing, the load factor ranges from 55% to 60%, whereas if we allow 64 cache lines probing, its load factor is as high as 90%. However, note that as we allow more cache line probing, the overall indexing performance suffers from a larger number of cache line accesses. Now, let me conclude the talk. We designed and implemented Cacheline-Conscious Extendable Hashing. It has 3-level structure by introducing an intermediate level called segment, which makes effective use of cache lines. With this 3-level structure and lazy deletion scheme, we can minimize I/O and obtain the right optimal performance. By introducing the split body tree, we can update directory in a failure-atomic manner without explicit logging. The source code are available on this GitHub repository. Thank you for listening, and I'll be happy to take any questions.
Any questions? I have a couple of questions. It seems like your work would also be applicable to DRAM as well as persistent memory.
Yes.
I was wondering if you could comment on that.
Yes, it is applicable to the DRAM. except for the part we designed for only for the persistent memory. I mean, the binary body tree is only for the persistent memory, so we can remove that part, and except for that part, we can, everything else is applicable, and it performs very well in DRAM.
And have you done the DRAM-based experiments to see what the performance actually looks like?
Yes, there is a graph here. Yeah, the left graph on this slide is based on DRAM, and it performs very well. Yeah.
Okay, great. Let's see, one other question. You talked about utilization, and I was
Yes.
wondering if you keep performance constant, like between the best alternative to CCEH and CCEH, what does the utilization look like? So for the same level of performance, are you better or worse in terms of utilization than alternatives?
For the utilization, there is no difference for the CCEH and CCEH with copy on writes. However, it depends on the parameter of how much linear proving we allow for the cache lines. So, yes, in this graph, we changes a lot of parameters, and we changes a lot for this parameter k, the number of cache lines we want to linear prove. And there are graphs in the paper about it, but as you can see, as we increase this parameter k, we have higher load factors, but it performs worse as we increase this k parameter. It's on the paper. Please refer to the paper for the details. Yeah. Thank you for the...
Okay, thank you. If there are are there any other questions? Please.
And I have one question about your experiments.
Okay.
So in the 2017 that application-friendly hash for DRAM from Harvard University, they claim that the insertion latency of the COOP hash is higher than the pass hashing. But in your experiments, actually the COOP hash is better than the pass hashing. So why do we have different results?
It's because of the implementation of this pass hashing and the cuckoo hashing is different. What I mean by that is we use the path hashing and level hashing codes from the authors, and we write the source code for the other hashing schemes, and this performance difference because of the implementations are quite huge. So yeah, the details is on the papers. And if you want to know more about this, let's take it offline. Yeah.
Okay, sure. Thank you.
Yeah, thank you.
Let's thank our speaker.